example, single phase, the nearest example is your ceiling fan. Okay, so this is induction, single phase induction motor because it uses AC supply. Okay, and then we have also three-phase induction motor. So that one is more on for the industry usage and also used for the electric vehicle to drive your vehicle. Okay, so your electric vehicle always use induction motor to drive the car. Okay, but there is another modern motor type that we not covered here. Okay, I think most of you have seen, maybe know about this BLDC motor, or sometimes we call brushless DC motor. Okay, so have you seen or maybe know about this brushless DC motor, BLDC motor? This is a very modern type of a motor. So in your opinion, is it DC or AC motor? Brushless DC motor. Okay, DC motor. And then others opinion? So actually, this motor is actually is AC type. Okay, this BLDC motor is actually an AC type. So this is a very modern motor type. It is very rugged, very compact, and very lightweight. Okay, in terms of its volume, size, and so on. Very compact and very efficient actually. This BLDC motor, you can actually see its application in drone. Okay, for example, the DJI drone and so on. You have a very small motor, right? Actually installed at the wings. Okay, very small. So that is actually a BLDC motor. Okay, even though maybe it use a DC battery, but inside that drone there is a what you call the power converter that actually convert from DC power into an AC power. Okay, so this BLDC motor is used in the drone and also your what you call e-scooter or maybe e-bike, the electric bicycle and so on. Okay, so the motor installed inside your tire is actually this BLDC motor. A very compact and so on, so you didn't realize that there is a motor installed inside your tire. Okay, very compact. And then actually one type of the BLDC motor, also the very simple one is actually your CPU fan. Okay, because your CPU, for example, your Intel, your AMD Ryzen and so on, so it has a fan to actually to cool down the temperature. So that fan is actually BLDC motor. Surprise? Okay, so there is a size. Okay, as you can see, that is a very lightweight, very compact and so on. That is actually a AC motor actually. Okay, but very compact and so on. The name here, DC motor, because the structure is actually a DC motor. It's actually a structure is similar to DC motor, but it actually use AC supply to operate. Okay, so that just for introduction. Okay, so this one I think I can skip this one. This one also Just for your information, so we have the stator and rotor. So the rotor is the part that we rotate. Depending on, because for the rotor itself, it has a winding. Stator also has a winding here. So the rotor has the winding. So depending on the type of the winding, so we can have two different rotor type, which is the squirrel cage rotor and the wound rotor. Okay, but mostly the industry use a squirrel cage rotor for their induction motor. Okay. And this is the cross section of the induction motor. So this is the stator and this is the rotor. So as you can see, stator is the stationary part, where the rotor is actually the moving part. And between here, as you can see, this is an air gap. There is no electrical connection between stator and rotor. And as you can see here, also this is a slot where we slot in the winding, the copper winding here, and also the same with the rotor. Okay, we have the slot to install the winding here. So this is the squirrel cage rotor type. And as you can see here, we have installed a blade. Okay, so this blade will actually also will act as a fan to cool down the temperature of this rotor. Okay, so when it rotates, so it will produce mechanical power, and at the same time, due to the rotation, we will actually use this blade to cool down the operating temperature of the motor. And then this is the wound rotor, so there is a different structure. And so this is the three-phase. Since this is a three-phase, so the stator here can be either, and the connection can be either in the Y connected or delta connected. And this is the induction motor operation. I think I can skip this one. So the main point or the main keyword here is the rotating magnetic flux. Okay, I hope you have already watched the video. The animation is the best way on how to explain about this RMF and so on. Okay, I can, this one. Okay, I can skip this one. Okay, so actually when there is a rotation and so on, so there will be a voltage induced. Okay, there will be a voltage induced at the between this air gap, and this voltage induced can be calculated. Okay, it actually depends on uh, the rotation of the RMF, the rotation magnetic flux, the number of winding, and the flux itself. Okay, so this is RMS, so you need to divide by square root 2, and then this is actually the voltage induced for each phase. Okay, so this is voltage induced at the stator. Okay, and this is voltage induced at the rotor. So there are two. This is actually just like a transformer, because we have a stator and this is a rotor, and then we have N1 and then N2. It depends on the winding. So this one is E1 and then this one is E2. Okay, so but the only difference is that this is AC circuit. So this stator will actually have their own frequency. Okay, and usually this frequency is same with the frequency supply. So if your frequency supply is 50 hertz, so your F1 is actually also 50 hertz. And then transferred to the rotor. So the rotor will also induce a voltage, which is you can calculate by using this equation. And as you can see here, okay, we have F2 frequency here. So actually the rotor is actually operated at different frequency. Okay, because based on the video that you see, the rotation, it will induce a voltage. Okay, this is AC. This is all AC, actually AC voltage and AC current. So AC is a cyclic, meaning that you have a frequency. So for the stator, so the frequency is equal to frequency supply, and the voltage induced is actually depends on this. Okay, while at the rotor side, the voltage induced is depends on this, and this rotor circuit will operate as a AC circuit, but with a frequency of F2. Okay. Okay. This one quite complicated. Okay, just to have you know about several parameters that very important, which is this one. The first one is what we call uh, sleep. Okay, so sleep is actually the ratio between synchronous speed minus the rotation of the motor over the synchronous speed. So what is the synchronous speed actually? The synchronous speed is actually the synchronous. It's actually the speed of the RMF, the rotating magnetic flux that induced at the stator. Okay, so because if you can see from the video, okay, the stator will produce flux, and this flux, because your current, your voltage is AC voltage, where sometimes it's positive, negative. So it's actually will produce a rotating magnetic flux. Okay, that will actually looks like it's actually a rotate. It actually rotating inside the stator, and the speed of this flux rotating is called synchronous speed. So this synchronous speed can be computed by using this equation: 120 multiplied with the frequency supply over P. P is actually number of pole. Okay, number of pole. This one is for AC motor. This pole is actually imaginary pole. It's different with the DC motor. So where this is for the DC motor, we have like this. For example, we have north and south. We have winding, right? From this is the what you call the field circuit, and then this is rotor. So this rotor is actually what you call the armature circuit. So this circuit, field circuit, we have north and south. This we call two pole structure. If you need to have four poles, meaning that you need to have this one, and then there is a winding also. So this will create north and south. So this one we call four poles. Okay, but in AC machine or AC motor, this pole is actually imaginary. It's actually you need to look at the video. The video actually explain the about this pole. Okay. So the synchronous speed or the speed of the rotating flux is depends on this equation. You can calculate by using this equation. 120 multiplied with the frequency supply over the number of pole. Okay? So that is your NS. And the units is actually in RPM. Okay? So NS minus NM. Okay, so NS minus NM, this is what we call sleep speed. Okay, so meaning that sleep is equal to sleep speed over MS. Okay, so sleep here is actually a ratio. There's no unit, and it can from 1 to 0. Okay, so when S is equal to 1, so when you put here S is equal to 1, meaning that your motor speed is 0. Meaning that when S is equal to 1, your motor is actually in a stationary position. No rotation. Okay. And when your S is equal to 0, meaning that your motor speed is equal to your synchronous speed. So that is about sleep speed, and synchronous speed. Okay. And then another point is the frequency that induced inside the rotor. Because we already know here, we have stator, we have their own frequency, and the rotor circuit have also their own frequency. So what is the frequency of this rotor circuit? You can compute by using this equation. So the frequency induced inside the rotor is S multiplied with the frequency supply or your frequency stator. So that is the frequency inside the rotor. Okay. The third one is the induced voltage at the rotor side. So as you can see here from my previous circuit here, uh, you have E1 and E2, right? But since this is a rotating part, so actually the voltage induced for this rotor is depends on the slip values. So I need to have S multiplied with E2. E2 is actually a voltage induced when S equal to 1. Okay, during stationary, the voltage induced is equal to E2. When it start rotating, so it is no longer equal to E2. It depends on the slip. So that's why the voltage induced at the rotor is depends on the slip. So also for the frequency. So the frequency also is depend on the slip. The frequency of the rotor is SF1, while the voltage induced inside the rotor is also depends on the slip, which is SE2. Okay, so we have frequency for the rotor and the voltage induced inside the rotor. Okay, so this one is, I think, is not very important. Okay, so I just skip. So sometimes the sleeps or the sleep speed and so on is actually referring to the radian per second. So this one is NS. Okay, this is all is is actually in the RPM unit. But sometimes they will also ask you to calculate the sleep, the synchronous speed in radian per second. So how can we convert NS into omega S? Okay, for example, if you have NS is around 8,000 RPM, so what is the radian per second value? So it's very simple, just multiply with 2 pi because one rotation is equal to 2 pi radians, okay, over, because 1 minute is equal to 60 seconds. So just multiply this one. So you will have the your values in radian per second. Okay. So this one actually similar to this one. Okay, but in the units of radian per second. So I think you can ignore this one. Okay. Especially this one. I think this one can be scrapped out because I think if you read this, you will be confused. Okay. Because one more thing that I want to highlight that for the synchronous speed, which is 120 multiplied with the frequency supply over P. This P is actually number of pole. Okay, but there is also a textbook or maybe another reference book that use NS is equal to 60 multiplied with frequency supply over P. Okay, please don't be confused. This P, if you are using 60, P is actually not number of pole, but it's actually pair of pole. So as you can see here, we have this one. So I don't want you to be confused. So I just use this formula instead. Okay, just but you let you know that if you facing these books with 60, so make sure that I just want to highlight that this P is not number of pole, but it's actually pair of pole. Okay, so but in our syllabus, I think we only use the first one. Okay, so please use one. Okay, so next one example, which is I have already shared with you. I think this one E is actually just skip here. Okay, so a three-phase 100 horsepower, 460 volt. So usually since this is a AC three-phase, so usually this one is a V line. Okay, V line. Because our plug at home, 240 volt RMS is not V phase, it's actually V line. Okay, so actually if you are from your source is from the three phase, so usually it is referring to the voltage line. And then the pole is 4 pole. The frequency supply is 60 hertz, so this is your frequency supply. Deliver a rated output power at sleep is equal to 0.05. So determine the synchronous speed and the motor speed. So the synchronous speed, which is NS, very simple, divided by number of pole. So your frequency supply is 60 hertz. So this one is actually 1800 RPM. Okay. And how to obtain the motor speed? This motor speed you can obtain by using the sleep. This sleep is actually the difference between motor speed and synchronous speed. So sleep 0.05, use this equation, ns minus nm over ns. Okay, so ns is 1800 minus nm over 1800, so 0.05. Okay, so from this equation, we will obtain that your motor speed is 1710 RPM, which has been given as an answer here. Okay, can you all follow? Okay, next is B, the speed of the rotating air gap field. So as mentioned before, the speed of the rotating air gap field is actually referring to the synchronous speed, because synchronous speed is actually your flux speed, right? Your flux, rotating flux that inside the rotor, inside the stator. So the same flux is actually rotating at the air gap. Okay, so meaning that the speed of the rotating flux is equals your synchronous speed, which is still 1,800 RPM. Okay, and so this one is actually your is equals to ns, which is 1,800 RPM. And C is the frequency of the rotor circuit. So the frequency of the rotor circuit is equivalent to F2, which is SF1. So S is given 0.05 multiplied with your frequency stator, which is equivalent to supply. So you will have your value of 0.05 multiplied with 60 hertz. So it is 3 hertz. So this is the frequency at the rotor circuit. Okay, please be mentioned that this motor is AC, so your stator circuit will operate at 60 hertz, while your rotor, because your rotor also have a winding, so it has their own circuit. Okay, so it will actually operating with 3 hertz frequency. And next one is the sleep frequency in RPM. So sleep frequency in RPM meaning that it is sleep speed actually, which is ns minus nm. Okay, so 1,800 RPM minus 1710. So this one is actually 90 RPM. Okay, so this one, we just ignore this one. We go for F. Rotor-induced voltage at operating speed if the stator to rotor turns ratio is 1 to 0.5. Rotor-induced voltage at operating speed if the stator to rotor turns ratio is 1 to 0.5. 1 to 0.5. Okay, so I think it's actually like a transformer. We have voltage induced at the stator over voltage induced at the rotor during standstill. Okay, E2 is actually a voltage induced at the rotor during standstill, no rotation. It's not start rotating. So it's equals to 1 over 0.5. This one is actually ratio of the winding. And E1 here, we assume is equal to, this one is your V line. So this one is actually phase values. So you need to convert into V phase first. So 460 over square root 3. So this one should be 460 over square root 3 is 265.5. So this one is V phase. And we assume that your E1 here is equals to voltage supply. Okay, so my E2 induced is equals to 0.5 multiplied with 265.5. Okay, so this one will be 132.7. Okay, so this is the voltage induced inside the rotor during standstill, meaning that S is equal to 1. So right now, we want to see what is the voltage induced during the operating speed. So the operating speed is actually during sleep is equal to 0.05. So meaning that the voltage induced at rotor is actually you need to SE2, which is S is 0.05 multiplied with E2 during standstill is 1227. So this one is equals to 6.64 volt V phase. Okay. I hope you understand this one. Okay, because the voltage induced at the rotor and the frequency is depends on the sleep. Okay, S E2, and what is E2 is actually the voltage induced during S is equal to 1. So the relationship between E1 and E2, you can always use this formula. Okay, so for example, I have used this one, and we assume that E1 is actually equals to voltage supply voltage phase. So you need to convert into a phase and then use this equation. Then I will obtain my E2 during standstill 132.7, and then referring to the speed. So you need to multiply with 0.05. So this is the voltage induced. Okay. So as you can see, during standstill, the voltage induced is very high, but when your motor is speeding at the rotation with a small slip, the voltage induced will be will actually reduce. Okay. Yes. The speed of the flux rotation is always maintains at 1800 rpm regardless of sleep values, because this synchronous speed is is actually depends on this formula 120 multiplied with frequency supply over number of pole. So it always maintain. There is no, as you can see, there is no variable that we can manipulate. Okay, is fixed here. So meaning that this rotating speed of the flux speed RMF, rotating magnetic field will always maintain at these values. Okay. The only that actually will actually vary is actually the rotor, because this rotor voltage induced, the frequency, the current, and so on is depends on the sleep. Okay. So if your sleep is very small, so the voltage induced very small, the current will be also very small, and so on. Okay, so we go for the equivalent circuit model. So this is the three-phase stator, and then as you can see, we have an air gap here, and then we have a three-phase rotor. Since this is a three-phase, and we assume that this is a balanced three-phase, so our equivalent circuit model will be actually a per-phase equivalent circuit. Okay. And since, as you can see, we have stator and rotor, and then the air gap, and then we have the number of winding N1 versus N2. So this is actually similar to the transformer. So actually, the equivalent circuit per phase equivalent circuit is actually also equals to the transformer. We have the primary leakage winding, the primary internal resistance, secondary internal resistance, and so on. Okay, but the only difference is that for the stator, the frequency is F1, but the stator, the frequency is different, which is F2, and this frequency of rotor is depends on the sleep multiplied with the frequency supply. Okay, the same also goes to the voltage induced E2. Okay, so this E voltage induced at the rotor is depends on the slip also. That is only the difference between induction motor and also the transformer. Okay, but still we need to go for the to derive this one. Okay, because the difference is actually because the rotor is rotating. There is a rotation motion there instead of static. So there will be some what we call difference, okay, between transformer equivalent circuit and the motor equivalent circuit. So this is the stator part. As you can see, we have R1 and X1, and then we have also core losses and magnetizing inductance for the stator, which is similar to the voltage to the transformer. So this is your voltage supply, and this is your voltage induced. But there's a difference where for the motor, the stator magnetizing current IM here is actually 20 to 50% of the stator current. Okay, unlike transformer, so transformer only use 1 to 5% from the stator, but for the motor, the IM is around 20 to 50%. So very big, the IM. Okay, and X1 is also very large compared to the transformer. And then this is the equivalent circuit at the rotor side. As you can see here, we have the voltage induced, which is depends on the slip values SE2. Okay, and then we have the current here and the inductance. The inductance value, as you can see, is actually depends on the slip values. Okay, because we know inductance XL is 2 pi FL. So right now your frequency is F2, right? So you know that F2 is S F1. So that's why we have XL. Okay. And we have R2 here. Okay, R2 here. And you can calculate your rotor current I2 by using a very simple Kirchhoff law here. Voltage over the total impedance. Okay, and the power of the rotor here, which is P2, is actually I2 square multiplied with R2. So this is the power input to the rotor. Okay, we know that we have stator. Okay, and we have the air gap here. So we have SE2 and I2 here. So to obtain what is the power that has been transferred from the stator, okay, this is what we call E2, which is also we can referring as a air power air, okay, which is the power rotor input, which is you can calculate by using I square R2. Okay. So this is the stator voltage equation, rotor voltage equation, and so on. Okay. So instead of writing your current equation as equals to SE2 here, okay, But if you are using this equation, if you are using this circuit, you will obtain your I2 is equals to SE2 over your Z, right? Okay. But the researcher, they have modified the circuit. Why don't we just put E2 here? So we factor out the S. Okay, we factor out the S. So for example, I2 is equal to SE2 over this one is R2 over S plus JX, right? This is the original referring to this. Okay, so when we factor out this S, sorry, this one, sorry, wrong. This one is actually SX, right? Okay, R2 plus SX. So when we factor out S, so this one will become R2 over S plus JX. So this one will be cancelled out. So that's why we have this one. So based on this equation, we can transform the circuit into this circuit. Okay, so E2 multiply with E2 here, and then right now X2, and then the resistance is a variable resistance, which is R2 over S. Okay, this one. So from here, we modify the circuit to be like this. Okay, we factor out the S. From here, we factor out S. So we will have this equation. And then this equation is translated into the circuit like this. Okay, so right now, our main concern is on the R2 over S here. Instead of R2 over S, a single resistant, because this resistant also have information about rotor losses and so on. What we do is actually we separate this. Okay, so R2 over S, we expand this one as equivalent to R2 plus 1 over S, R2 over S. Okay, so we can actually, finally, the circuit that we use is this one. R2, which is a fixed values, and a variable resistance here, which is if you sum up all together, you will have the original value, which is R2 over S. Okay, why we separate this? Because these values is actually referring to the rotor losses, while this one will actually go for the power output. So rotor losses is actually P is equal to I. So you need to I square multiply with R2. This is the rotor losses. While the power output, referring to this one, is I square multiply with 1 minus S R over S. So this is your power output. So that's why we separate this into two resistant values. So this one we're referring to the power losses inside the rotor circuit, and the other one is will actually referring to the power output. And this power output, as you can see, it depends on the slip values. Okay, so after you have we have discussed and derived, so this is actually the final equivalent circuit. So we have the stator, R1, X1, and then we have the core losses, which is represent the RC and XM, and then we have at the rotor side. Okay, so this rotor, as you can see, is referring to the stationary. So that's why you need to multiply a square. Okay, because this is actually referring to the stationary, to the stator. Okay, but as you can see here, this model is not convenient to use to predict circuit performance because you have RC, XM, and so on. So this circuit is very complicated. So what we do is actually this one is actually the same one that I have explained earlier. Oh, okay. This one actually is not very convenient. Okay, we will actually look at the most simplified version of the circuit. Okay, so this is the same thing that I have explained earlier, which is this is power rotor transferred to the rotor, which is uh, similar to the what you call the power air gap. Okay, which is you can calculate by using this equation. Okay, and as you can see, this R2 over S, you can expand into two elements, which is this one will give you the rotor losses, while this one will give you the power mechanical output. Okay, so this one is the P2 is actually your rotor losses. Okay, and this one is your P out. And based on this equation also, the P out can be also use 1 minus S P again. It's look complicated, but it need some time for you to actually blend it. Okay, I know. Okay, so P2 here is actually P2 here is actually P rotor losses. Okay, which is you can compute by using this one, or in terms of power air gap is just multiply with S. And the mechanical output, which is P out, is you can use this equation, or in power air gap is actually 1 minus S P air gap. Okay. Example 2. Oh, okay. I think we stop at example 2. Okay, and then maybe next class. Okay, for information, Monday class, there will be Monday class. The class will be cancelled because I involved with the capstone student presentation on the morning session. So please be noted, Monday class there is no class, so we will continue on the Tuesday. Okay, so example. Example 2 of the mechanical, a three-phase 15 horsepower, 460 volt. So this one is your V line, 4 pole. This is your frequency supply, and this is your motor speed. Okay. Delivers full output power to a load connected to its shaft. The windage and friction losses of the motor is 750 watt. So windage and friction losses, this one is mechanical losses we didn't cover in our syllabus. So determine the mechanical power. So this solution example have also been shared in your WhatsApp group. So mechanical power. So how to get mechanical power? The answer is given 11940 watts. The first thing that you need to do is to get the what you call the sleep. To get the sleep, okay, you need to get NS first. Always, I think, started with the NS. So NS is 120 multiplied with the frequency supply over pole, which is 4. This one, I think, will be 1,800 RPM. So your sleep will be one 0.04. So your sleep right now is 0.04. So what's next? The mechanical power, which is your P out actually. What information that you can use? Mechanical power. Right now we have obtained your S. Mechanical power. Mechanical power. Okay, find the power gap, correct. But the power gap, you need to use this one, I square R2 over S. But right now, S we obtained, but they didn't given R2. Hmm. This is example 2, right? Oh, I see. Hmm. How to get mechanical power? Also don't have any idea. My head right now is blank. Hmm. Mechanical power. So mechanical power. Uh, so actually mechanical power, you can use this one over 1 minus S P again, right? Rotor copper loss is actually P2 or P rotor loss is SP again. And power air gap is your input power actually. Okay, P air gap. Windage and friction loss. I think from this one, uh, I think there is information that actually there is an information that not available here. Actually, you can get from here. I think this question is not complete. It's not complete. So 1 horsepower is equivalent to what? How many watt? Can you Google? Is equivalent to 746 watt. Yes, I think yes. This question is not complete. 746 watt. So if you have 15 horsepower, so this 15 horsepower is equivalent to 15 multiplied with 746. So 11.19 kilowatt. Okay. So this is the output 11.190 kilowatt. Okay, and then we have friction losses, which is 750 watt. Okay, so the P out here, you need to 11.19 kilowatt multiply plus 750 watt. So you will obtain 11.19 kilowatt plus 750. So you have 11940. Okay, good. We have obtained this one. 11.94 kilowatt. So this question is not complete. It should give you the horsepower equivalent. So we have complete this one. Okay. So from that, we can get your power air gap, which is P out over 1 minus S. So 11.940 kilowatt over 1 minus 0.04. Okay, 11.940 kilowatt over 1 minus 0.04. So 12.437. Okay, this one. And then lastly, the rotor copper losses. So just multiply with S. So 0.04 multiply with 12,437.5. So the rotor copper loss is 497.51. Okay. So the only problem that this question is not complete because it should give the value here. 1 horsepower equivalent to what? Okay, So in terms of the power flow, okay, so this one is your P. This one is the P mechanical, P mech losses. Okay, so this one is your P out. And then from the P out here, you will have P rotor losses, P2. And then this is your P air gap. Okay, from this P air gap, you have what I call P1. This is the stator rotor, stator losses. And then finally, this is your P input. So in terms of the power flow, this is the losses and so on. Okay, you have flow here like this. Okay, so P out here is actually the P out without mechanical losses. Okay. Okay, so I think that's all for today. I think it's enough for you to try to first digest the equivalent circuit first, and then the power flow. So as mentioned earlier, so the calculation is not involved. Only involved is the equivalent circuit and also the power flow. But it's good for you to know about the equation and so on. Okay, so I think that's all for this class. And if there is no question, then we can dismiss. This is recorded and I will actually post it to you when it is available. Okay, so thank you very much.